Welcome, class, to Chapter 5, Sensation and Perception. Neurons inside your brain do not directly experience the outside world. Instead, they communicate with other neurons inside your brain. Your conscious experience of the world emerges really from this communication, all happening in milliseconds rather. We don't see the world as they are, we see them as we are, says Anais Nin. And if the doors of perception were cleansed, everything would appear to man as it is infinite, says William Blake. So we're talking about two concepts here of sensation and perception. Sensation is a sense organ's detection of external physical stimulus and the transmission of that information about this stimulus to the brain, whereas perception is the processing, organization, and interpretation of sensory signals in the brain. These processes result in an internal neural representation of the physical stimulus. And so, again, taking in the information from the external world, transducing it, and then there's some processes later in the brain that all happening in a millisecond that influence that perception or the sensations, the perception of those sensations. M.C. Escher plays on this idea here of the idea of perception and how our brain, when we talked about Gestalt, sees things as either a figure or a background, but not both. And we talked about the idea of the Dalmatian or the cubes, how you can see the front as the front, or then you can also look at it as the square in the back. And so right here you can see the stairs going both down and up. And then here he plays on the perception that our brain uses, right, in terms of being able to see three dimensions, plays on that as well. Looking, as you can see here, the bricks are kind of going down, and it makes it looks like the water could actually be going down, but it's actually going up, and the different ways that the columns are set. In this example right here, this arrow looks like it is shorter than this line right here. If you look at in terms of just the straight line right here, but in actuality, this straight line and this straight line are the same. It just you perceive it as different, and so there's another way in which perception influences our sensation of the world. Thus, we don't see the world as it is, but we see it as we are. And from sensation to perception, just some ideas of the sensory receptors, sensory organs that detects physical stimulation from the external world and change that stimulation into information that can be processed by the brain. And then there's transduction, which is the process by which sensory receptors change that physical stimuli into signals that are eventually sent to the brain. And then there's perception, where there's further processing that can influence those sensations. And that happens after transduction. And this kind of goes over it in your text, the idea of you got this physical stimulus, the traffic light turns green, light waves are the physical stimulus, the light waves are detected by the sensory receptors in the eyes. Sensory receptors translate the physical stimulus into signals. Those signals will become neural signals. And then the perception, the neural signals travel on the nerve fibers to the thalamus. Cortical in the areas of brain process the signals and construct a representation of the green light. The brain interprets the light as indicating to start driving, and all those processes really happen in a millisecond. This talks about, this slide right here talks about different areas of the brain related to perception. And as you can see right here, the perception of smell is located in the olfactory cortex in this area. The gustatory cortex, the perception of taste in this area. Perception of hearing in this area right here, primary visual cortex in the back right here, somatosensory cortex for touch, and then also for movement as well is right here as well. And that's not indicated on the slide, but it talks about really that there's different areas of the brain that are localized for specific tasks, if you will. And in this sense, it's the tasks related to our senses and taking in, perceiving the information from the external world. Thus, consciousness, if you will, doesn't exist in one area of the brain, but exists in multiple areas of the brain. And consciousness is just that experience that you have at this moment when you're paying attention to things or not paying attention, but in that waking state, right? And you have different experiences depending on different areas of the brain that are being stimulated or are being active. The absolute threshold is the smallest amount of physical stimulation required to detect a sensory input half the time it is present. And the fascinating thing about this slide, I find, is just the absolute threshold to detect input for each sense. The minimum sensory input required for detection of 1 teaspoon of sugar, and it would be in 2 gallons of water, where people notice it half the time. Hey, there's sugar in this water. And under that, they wouldn't notice that. 1 drop of perfume diffused in the entire volume of 6 rooms, so pretty good for smell. Yeah, that's why a lot of people are always complaining about, too much perfume, if you will. Certainly, if you're waiting tables, good to not use perfume or cologne. And this one's gross, the touch one, the fly's wing, Can we choose something else that's like really small? Fascinating right here, candle flame, 30 miles away on a dark, clear night. Fascinating that we can see that, right? Difference threshold, the minimum amount of change in a physical stimulus required to detect a difference between one sensory input and another. The idea is pick up something that weighs 1 ounce versus 2 ounces, and you can really tell the difference very easily. And that's because of Weber's law, and that's the idea that it's based on proportion, right? The difference is right there versus a fixed amount. A fixed amount of 1 ounce versus 2 ounce is 1 ounce, right? But they're just so different because you're holding them both together. You can totally tell the difference in terms of weight. But if you picked up something that was 5 pounds versus 5 pounds 1 ounce, add an extra 1 ounce, that fixed amount, you wouldn't be able to tell, because proportionally speaking, they're both pretty heavy, and you're like, Okay, so we got that right? Yeah. Signal detection theory. Detection of a faint stimulus requires a judgment. It's not an all or nothing process. Signal detection theory helps us understand how a person can be biased towards either responding or not responding despite being given the same amount of sensory input. And they give examples of that. Of course, if you're rewarded to find an error, you're going to find more errors. If you're punished for finding errors, then you're going to be prone to finding less errors, right? And so that influences your motivation. Obviously, your experience of detecting things is going to influence that, as well as your attention if you're not paying attention, in your training. And so they really talk about the signal detection theory is that there are some afterwards processes, right, that go on to determine whether or not you notice the signal. Sensory adaptation also, so we have adaptation, which is really cool, right? You get used to sounds, so the sounds don't bug you as much. Decrease in sensitivity to a constant level of stimulation. Eventually you get used to the construction noise outside, or the fridge noise, or the freeway noise outside, where you could even think it sounds like the ocean, perhaps, and there's like a loud horn or something like that, and you're like, when the stimulus stops, we notice the stoppage. For example, we notice the quiet after construction, or fridge noise stops, for example, and we're like, whoa, it's really nice without that fridge noise. Okay, and then the sensory receptors in our eyes detect light. So I'm going to go over one example of the senses. So we've got see, smell, hear, and you've got taste and touch, right? And we got pain. I think it goes over pain as well. But we're just going to go over seeing, and let's take a look at it. So physical stimulus, the sensation, the transduction, and the perception. We're going to kind of go over this, break it down. Let's take a look at it. So focusing light in the eye, light waves pass through the cornea of the eye, right here. And that's a clear membrane that helps focus the image. Light waves then pass through the pupil, that's the hole in your eye. The iris, the circular muscle, gives light their color, gives your eyes their color, and controls the pupil size, determines how much light enters the eye. And then you have your lens, which is adjustable, kind of stretches, and transparent structure behind the pupil. And there it is right there. And this structure focuses the light on the retina back here. There's the retina. And it flattens when things are farther away and thickens when things are close to you. The retina, the thin inner surface of the back of the eyeball. This surface, contains the visual sensory receptors, the rods, and the cones. There's 120 million rods and 6 million cones. The rods are concentrated near the retina's edges, respond well to low levels of light, night vision, do not support color vision, and poor at providing fine detail. So they're more on the edges, whereas the cones, primarily responsible for vision under bright conditions and for seeing both color and detail, they're near the center of the retina and a small region called the fovea, where cones are densely packed. Cones are more scarce near the outside edge of the retina. And information about what the eye has sensed is delivered to the ganglion cells, and they are the first true neurons of the visual system, as they do fire action potentials. The axons of each ganglion cell are gathered into a bundle. This bundle is called the optic nerve. Okay, so that's a good thing right there. Really small, you can see, and not a very good slide for that. Point out to the optic nerve. Should have a better slide for that. But anyway, there are blind spots in your left and right visual fields where the optic nerve exits the retina. So obviously there's the optic nerve, there's the place, and you can't have, rods and cones right there because there's bundles of nerve fibers that are going in there, and that's your blind spot. That shows it a little better, I guess, the optic nerve. But you know where that is, right? The back of the eyeball, where it's got, it's like the connection. You can't have eyeballs just floating out there, right? You got to be connected to the brain, right? Because you got your sense organs, and their sense organs, that looks a little weird. And the sense organs are taking that information into the brain, right? Where your consciousness exists in the brain, processes everything. Your brain is processing things right now, right? All your experiences, all your memories, your information or knowledge of language in an instantaneous moment is being understood right now, right? Language and from all that, and it's by your brain processing. It's fascinating, right? Half the axons in the optic nerves cross to the other side of the brain. The rest of the axons stay on the same side of the brain. The point where the axons cross is known as the optic chiasm. Remember that information then goes to the thalamus and travels to the primary visual cortex and the occipital lobes. Signals from the visual field are processed in the primary visual cortex, that is the opposite of the visual field. And remember, we talked about that with the split brain patients, how they see, and you do too, information from this side is going to be processed on the opposite side and vice versa, right? And same with touch too as well. It's going to go to the opposite side. And this kind of goes over all of the process there. This kind of shows you the nice, the optic nerve. There it is again, huh? And then it crosses the optic chiasm and goes to the opposite sides of the left or right primary visual cortex. Probably won't go over the aspects of color too much in terms of the nitty-gritty on it or testing on it. You're like, okay, fast forward this slide, right? But there's different types of electromagnetic waves, of which visible light is one of them. And they are different by wavelength. And so if you can just take a look at the visible light, which is right there, that little rainbow, somewhere over the rainbow, right? The brother is, don't you love that song? Bust out the ukulele. For humans, visible light consists of electromagnetic waves ranging in length from 390 to 700 nanometers. Again, they're different from wavelength to peak. And so that's how you measure the different electromagnetic waves. And then they are also within the visible spectrum, different wavelengths, and that determines color and hue and saturation. Amplitude is the height of the light wave from base to peak. Base to peak, base to peak. There you go. Wavelength, the light wave is the distance from peak to peak. So you can see a long wavelength, short wavelength, high amplitude, low amplitude. Oh yeah. Hue refers to the difference in the particular colors within the spectrum, and saturation has to do with the intensity of the color. And the trichromatic theory, you won't be tested too much on this, but essentially that there are 3 types of cone receptors in the retina that are responsible for color perception. Each type responds optimally to a different but overlapping range of wavelengths. And so you can see the S cones, M cones, and L cones. Probably a little too much detail for what you need to know. There's also an opponent process theory, which is these are just ways to explain that things don't quite fit in with the previous theory of the trichromatic theory. And I like to throw the slide in because you can do pause slide, right, and pause the vid, and then do this little technique where you stare at that for a while. Just the dot. Stare at just that, like a minute or something. Then you look over here. I think you can do even less than a minute, or 30 seconds, and then you see the American flag. You're like, why do you see that? Well, you know, you're looking at this, and then the neurons for those things are firing. And then when you look at this, maybe those are like over firing, and so now they're under firing, and then the opposite colors are firing now. Kind of like the waterfall effect. That's what I think the whole thing is about that. We're going to go over that in a sec. It's kind of cool. I always thought, I was like, whoa, is there something wrong with my brain? Am I tripping? Was it like something I did in college or something like that? Or at the time of college, looking at the waterfall and then looking at the wall and seeing it move the opposite way, what's going on? And then I read about that waterfall effect and I was like, dude, okay, not true. Very little of what we call seeing takes place in the eyes. What we see results from the processing in the brain. Perception is more than simply gathering sensory input. Gestalt, or the organized whole, remember we reviewed this? The idea is our brains use a number of built-in principles to organize sensory information and see things not as their parts, but as a whole. And it really helps us to make sense of the world and to see things in a regular way, in a way that's easy for us to process things. It is the way that the brain works. Figure ground, organize visual features into an object which is a figure that is distinct from the background. And mentioned this earlier, right? But it's the idea, do you see a vase or 2 faces? And do you see the young woman or the old lady? Pause for a second, take a look at that one. Which one do you see? Okay, the young lady that's her eyelash right there, and she's got red hair, and that's her chin line, and she's looking away. And the old lady that's her mouth, which is the necklace thing or the choker thing of the young lady. That's her mouth. That's her nose, the chin line of the young lady. And that's her eyes, which are the ear of the young lady. And she's got gray hair. And threw in some Pink Floyd The Wall because, you know, under different perceptual influences, you can have different perceptual experiences, and that's played on in Pink Floyd The Wall, where they put things that are can be seen supposedly by certain students that have reported this under certain conditions. Grouping, to form a coherent, unified image of what you see, the brain must decide what parts go together. Gestalt researchers identified how the brain groups things together, and so these are just ideas that what they found is the way that the brain works in terms of giving you a perceptual whole that makes sense. Proximity is one idea. Close figures are grouped as an object, so we see these 16 dots as 3 groups of objects. Similarity, similar figures are grouped in an object, so we see this rectangle as having 2 locked pieces. Continuity, intersecting lines are interpreted as continuous, so we see the green bar as one piece that continues behind the purple cylinder, not as all of a sudden the world is like breaking up, now there's 2 pieces just because it goes behind something. Closure, figures with gaps are interpreted as complete, so we see the figure as one whole triangle, as opposed to broken up, just this triangle, and this triangle, 3 separate triangles. Okay, again, giving us that whole perceptual experience that kind of makes sense and is orderly. illusory contours. Contours are perceived even when they don't exist. So we see contours of a square here, even though it doesn't exist. Again, we're pattern seekers, our mind is, and it's easy for us to be able to be successful in the world, really, by seeing things in a way that makes sense and is orderly. There's bottom-up processing and there's top-down processing. Bottom-up processing refers to processing really begins with the external world and the sensory input, which is detected by the sensory receptors, processed from these basic lower levels to a higher, more conceptual levels within the brain. Then there's top-down processing. So that's kind of what we've talked about already, is the bottom-up processing, right? That whole process of the sensation to eventually being transduced and that information going into the brain. But what happens after that transduction? What's going on? There's perception that's going on, right? And there's some things that we do that start to put order into that sensation, right? And then there's also other things that we do that we expect things to be a certain way, and that really helps us to understand language. It helps us to understand a complex world in terms of sensations that are coming in, and us being able to perceive things on a regular basis and not be overwhelmed. Perception, top-down processing, refers to the perception of objects is due to complex analysis of prior experiences and expectations within the brain. This analysis influences how sensory receptors process stimulus input from the environment. And they give the example of the pilot in Antarctica that flies into a mountain, and he thought he was somewhere else, and so he didn't see the mountain, even though he saw it, but he didn't see it because it didn't exist in his mind, because he thought he was somewhere else. So if you want to take a pause and click that link there, you can see how other ways of top-down processing can influence your perception. The light of the 3D world travels to our eyes and is presented on the retinas in 2 dimensions only, like a photograph. So how does the brain perceive depth? Well, it uses binocular depth cues, and you have to remember that your eyes are a particular distance away from each other, and your brain knows that, so it can do basically some geometry and a little calculus to figure out depth, and that's what it does. Cues of depth perception that arise because people have 2 eyes. Each eye has a slightly different viewpoint. There's a binocular disparity between the 2 images caused by the distance between the eyes. The brain does geometry to figure out the distance and provides depth perception of the objects close to us. We also use monocular depth cues, also known as pictorial depth cues. Cues of depth perception that are available to each eye alone. And artists use these all the time to change what appears to be a 2-dimensional flat space, right, into a 3-dimensional thing. And how do they do that? Well, they do it by various ways. Occlusion, a near object blocks an object that is farther away. Height and field, objects that are lower in the visual field are seen as nearer than objects that are higher in the visual field. Relative size, objects that are farther away appear to be smaller. Familiar size, we know how large familiar objects are, such as a car, so we can estimate how far away that they are by the size of their retinal images. And that is played upon when we see the full moon. And why does the full moon look so big when it's at the horizon? Because it has to do with the familiar size. We're not used to seeing things that big on the horizon, and so when it's on the horizon, we make it look even bigger. But the moon doesn't change size. Like, what? That's kind of trippy, right? Oh, top-down processing right there, right? Okay, linear perspective, seemingly parallel lines, sidewalk appear to converge in distance. And of course, artists do that too, right? They'll draw something on the sidewalk that totally looks like you can fall inside the hole or something like that and get pulled down by, I don't know, Hades workers or something like that in some Dante's Inferno. Linear, we already did that one. Texture grading, uniformly textured surface recedes as texture continuously becomes denser. For example, the pattern on the pavement. You see more texture in the front than you do in the back, right? And we've got Willy Wonka. Is the room getting smaller? Some just cool perspectives here of, the blue atmosphere in the background makes things look farther away too, or the purple. And then the moon as well. There's the waterfall effect, the motion after effects. Gaze at a waterfall for a long time. Then when you look away at the stationary scene, it appears to be moving in the opposite direction of the waterfall. Motion after effects are strong evidence that the motion-sensitive neurons exist in the brain. Visual cortex has neurons that respond to movement in a given direction. When you stare at a moving sensory input long enough, these direction-specific neurons start adapting to the motion and become fatigued, less sensitive. Once the sensory input is removed, the motion detectors that respond to all other directions are more active than the fatigued motion directors. Thus, you see the new scene moving in the opposite direction. So next time, watch a waterfall for a long time, and then look at the wall, something flat that's not moving right next to it, and then all of a sudden that wall will be moving the other way, and you'll be like, whoa, dude. Your friends will be like, no way. And then you'll be like, it's okay. It's just called the waterfall effect. And then they'll think of you as like this like super sage. Oh my gosh, I have to consult with this waterfall effect person. Stroboscopic motion, very cool to do. Remember when you used to draw like the little stick surfer guy and do the little book where you just flip the pages of the book, right? And it looks like it's moving. Well, that's what movies are made up of. They're still images, and one of which is each slightly different than the one before it. When the series is presented fast enough, we perceive the illusion of motion pictures. This perceptual illusion is called stroboscopic motion. Wah, 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 wah. Okay, so probably end here because I hear that it's a little long for you, you know, to do these super long 40-minute videos or whatever. I'm hearing you. Oh, we'll end at hearing right here. But check out the rest of the chapter, and I will see you for chapter 6. See ya.